what people said in the timer. Okay. Hoo-hoo, 11 to 8. This is pretty close to split 50-50. 11 to 8. We had a couple people walk in just now, so I think we're going to do a revote. The way I would think about this is I would ask yourself, what happens if they are 100% or 0%? This is like a good way to figure it out. So we're going to do a revote here and see if we can get a majority in one or the other. So think about what happens in real life if something is 100% or 0%, and like what that means for trying to estimate the likelihood. Remember, this is all about likelihood. Yeah, all right, that's my hint. Think about like 0, 100, 100, 0, this kind of stuff. And I'm going to revote it and give you another minute to try to do it. I suppose this is hard it's hard to keep people from peeking at their notes. But let's try and see if we can get a majority on one or the other. Okay, I'm going to duplicate this and then this one. Okay, here it is again. We'll go another minute, see if you can figure it out based on the hint that I gave. Okay, let's see what we got to this time. Drum roll. Okay, this time people are moving slowly into this category, and that is the correct answer. The way I remember this category is that P is the true probability. That could be 100% or 0%. And that would mean that like your observations are always one thing or the other thing. But P hat should never be 100% or 0%. And the problem is if your P hat is 0% or 100%, then your likelihood will be like 0. Like you'll see something that you had a likelihood of 0 to happen. And that would be really bad. So this is the main way I remember it, is I remember that P hat can't be 0 or 1, but P can be 0 or 1. And in fact, P being 0 or 1 comes up in a very particular way that I will show you now. That is really important. So let's open up what we were doing last time with the likelihood, which is here. No, yeah, this page. And the timer is vexing me. Okay. It was this formula. So this was how we calculated the cross-entry loss in practice for heads and tails, and we did the number of heads divided by the number of heads and the number of tails. And this really is representing the P that we saw in the wild, right? We saw the fraction of heads that we saw was the number of heads divided by the number of heads plus the number of tails. But in practice, when you go to calculate this, you're going to calculate it by doing a sum. And that's what I'm going to write out now. So let me actually copy paste this formula, and then let me try to do a sum. Oh, that was a funny way to do it. Maybe I can do it like this. Can I do this? Okay. Copy, and then paste. Okay. So this is the formula we had before. And let me erase this little guy. So I claim that you can get this by doing 1 over n, and then you do the sum of xi times the log of p hat plus 1 minus xi times the log of 1 minus p hat, where xi equals 1 if ith flip is a heads. Let me write it as a little. Yes, I knew this would happen. Did it screw up over there? Okay. I'm having a wire issue here where the wire is not working. Let me briefly fix this. Normally you poke it and it will work. All right, let me share with the class. This is what I see on my screen. Not ideal. Okay, let me poke. This is like, in like the 50s, you like hit the TV. Okay, we're back. Okay. So it should be, are we back? We're back, except the mouse doesn't work. This is annoying. Okay, now we're really back. Okay. It's xi is 1 if heads and 0 if tails. So xi is like the one hot encoding of the heads or the tails, and you can write it like this. And by doing the sum of the xi's, I going from 1 to n, then you're adding up the heads, right? So the sum of the xi, this will add up to the number of heads. The 1 minus xi will add up to the number of tails. And you can really think about this. This is the cross entropy loss with one example, the cross entropy loss of xi p hat, right? So you can think of xi as like, for an individual coin flip, it either was exactly heads or exactly tails. And so you can say the probability for one coin flip is either 100% or 0%. And the cross entropy loss formula makes perfect sense over here. And you average it over all your things. So that you can think of this as the average of the cross entropy losses. So the average cross entropy loss. And it makes perfect sense. So this formula is used all the time and is a really important way to understand these things. Every individual example gives you one little data point that you add up. And your p hat is trying to balance, right? Your p hat is trying to match the average as well as it can for all the possible things. Okay, that was a little recap of p versus p hat from last time. We're going to move on to doing it. Last class we did binary. Now we're going to do multi-class. So the next couple of questions are all going to be about multi-class classification. What happens if instead of having 2 classes, heads or tails, you have 3 classes, red, blue, or green? But any questions or comments about anything so far? Okay, let's do some multi-class classification. And to do the multi-class classification, I have more questions. Okay, so the first thing is, how would you do multi-class regression? Well, in regression we had the mean squared error, which was y minus y hat squared. If you had multiple things you needed to estimate, one way you could combine them would be to do the sum of the squares. So maybe instead of estimating just the height of a person, you need to estimate their height and their weight. Then you would say, how close were you to the real answer in their height? Square that, add that to how close were you to the real answer in their weight. But how do we do that with multi-class classification? So you have k classes, red, green, or blue, that'd be k equals 3. So you have 3 probabilities now, p1, p2, p3. How do you write the loss function? And here are some different options for you. How would we do a multi-class classification? And again, this was sort of related to the video on multi-class classification. If you think about where did this stuff come from, you should be able to figure this out. Okay, let me give you a few minutes to work it out, and we will go from there. Feel free to chat with your neighbor or write down some hints. Remember, this is a likelihood. Can you write down the likelihood of the things that you would see? Okay, 30 seconds left. Take a stab at it if you don't know for sure. Okay, time is up. Time is up. Okay, let us see what we got to. Okay. 7 people are in this formula. 12 people are in this formula with the 1 minus p. 3 people are in the difference squared. The difference squared, unfortunately, is incorrect. So this one is tempting because it's so simple, it's so nice. But once again, you really should think of these things as coming from a likelihood. And when you're dealing with things that are one class or another class, then the likelihood does not depend on the square. The likelihood depends on like p to some power, and the log likelihood is going to have some logs in it. So this thing really comes from the sum of the squares, comes from the likelihood of the exponential random variable. Let me do a little thing. So if you have e to the minus y hat 1 squared, this is a Gaussian with one thing. This is the probability density of a Gaussian of y1. And you have another one, y2 minus y hat squared, and they're independent, then you would multiply them. This is the density of a Gaussian y2. These are probability density functions. So when you multiply them, you add the exponents, and because the Gaussian density has this exponential in it, the log likelihood gives the loss. Log likelihood is the loss, and that will just be the difference squared. So the e's go away, and you get this kind of thing. The log likelihood, and remember the log likelihood and the loss are related by a minus sign. You put the minus sign back in, you get exactly what was there. Unfortunately for us, we are not in this situation. So in multi-class classification, it is not like this. We have probabilities, and the probabilities depend on things with powers. Those are the probabilities for classes are different. Okay, so that one is not correct. This one's not correct. With those 3 people gone, it's a pretty even split between this one and that one. So let's do, again, a revote. What is going on here? I think a good way to think about it is what happens when there's only 2 classes. If k equals 2, which one will give the formula that we had before? That's a good way to think about it. Let me give you that hint, and I will set you loose once again to try and do it another time. Let's see if we can get a consensus. Okay, give it a try. Think about it. This is it's easy for me to tell you. I think you'll learn it better if you think about it. Okay. Last time, it was pretty split. This time, do we have a consensus? No. Are 2 people asleep? Okay. This is interesting. So we're on 2, 4, 6, 8, 10, 12, 14, 16. Okay, I don't know who's asleep. Interesting. I did open a new one. Okay, yeah, all right. Okay, 2 people are asleep. People are split. Let's chat about it. Did it go down or did it go up? I think it was less split last time. Now people are more split. Okay, this is good. This is a good moment. Something's going to happen. Someone talk to me. Someone who changed votes. Why did you change votes? What was your thought? Put your hand up if you changed votes. Only one person changed votes. Okay, then you have to tell us. Why did you change votes?
Actually, I was feeling that the formula was a bit too complicated. Actually, it's not logical.
No, not logical is okay. I mean, we're humans. We're not logical. I don't think you can escape being a human unless you have a way to convert yourself to a robot. But not logical is the way we're going to go. So yeah, tell me how did you think about it?
It seemed less complicated.
I see. You wanted the simpler formula.
Yeah.
And you said this top one is simpler. So you switched from the less complicated one to the simpler one. And that seems right to you. You're right. This is the simpler one. This is very good. You got it right. So congratulations. The simpler one is right. I think a lot of people, when they go to the multi-class one, they get bamboozled, and then they write this one down. Because this one looks more like the one we just had, right? This one looks like the one that I just did a second ago that I had on the board. And so it is kind of like a bit of a funny trick. Let's see, I'm sure I had it on the board. Yeah, okay, this one, right? But it's the simpler one. And so like a majority of people got it wrong. It is a bit simpler. And the reason it's simpler is there is a simple way to write down a multi-class probability. So again, let's set xi, let's make it be a one hot. How do I want to? Yeah, okay. Let's call it xj. And that makes up our i's and our j's. J, we're going to make it a one hot. So it's 1 if class of item is j. Okay, so it's like this, and it's 0 otherwise. I will warn you, this is a little bit different. So before I had an xi was the ith example, or the ith example. And this xj is talking about the jth class. The jth class. So this is 4 class numbers, number j. And this is really like a one hot. So if you had 3 classes, example, if there are 3 classes, it could look like x1, x2, x3 equals 0, 1, 0. And that means you are in class 2 and you're not in classes 1 or 3. So this is really the one hot encoding that we talked about earlier. And you can write the probability quite nicely. What is the probability? The probability that you are class j, you could write this as what? Well, you could say it's just pj. But see, the problem is pj is a little bit annoying because I want it to depend on these x's. X's are what I have. I don't want to say like pick out the j. So the way I'm going to do it is like this. I'm going to write pj as something very silly. Pj to the xj. You see, because if it's in class j, then xj is 1. And then pj to the xj is pj. So it's like what I did before. You could also write, this is going to seem even more silly, you could write p1 to the power 0. I'm going to multiply it by p1 to the power 0. Well, that's just multiplying it by 1. That doesn't change the answer either. And you can keep doing this. So what if instead of p1 to the power 0, I could write p1 to the power x1? Because you see x1 is 0. And this is a very silly way of writing it, but it works very nicely. If you take this to its logical conclusion, you'll write it like this. P1 to the x1 times p2 to the x2 times p3 to the x3 times ... all the way up to pn to the xn, where n is the number of classes. I guess I called that k. Let me rewrite it as k to match the question we had before. pk, the xk. K is the number of classes. Okay. And the point of writing it this way, it seems very dumb. Most of these are 0, right? Of x1 to xk, only one of them is non-zero. And the one that is non-zero is the one that goes with the probability we want. So the probability of being in class J is this crazy product. And the reason this is nice is because when I take the log, it's going to become a nice thing. So the log of the probability of class J Okay, let me actually make the notation match even better. Let's say the probability of class J given using P1 hat, P2 hat, P3 hat, all the way up to PK hat, and then there's hats everywhere. So this is saying if you have an estimate for all the different P values, the probability that you see class J with our estimates is this crazy formula. And then I'll take the log to get the log likelihood using P hats. And it's going to be a big sum. So you take the log of this whole big thing, and that becomes the sum of the logs. P1 to the x1 plus the log of P2 to the x2 plus dot 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 plus the log of pk to the xk. And now the exponent in the log jumps down as well. So this is x1 times the log of p hat 1 plus x2 times the log of p hat 2 plus dot 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 plus xk times the log of p hat k. I can try to zoom in a bit. Okay, so that's very nice. Most of these are 0. We're adding the number 0 to itself many times, right? All of the x's are 0 except for one of them. And the one of them is the class that we're looking at. Okay, so that's very nice. So this is the log likelihood. And you can write this in the formula as a simple sum, j going from 1 to k, of xj times the log of p hat j, which is the formula that we had before, except the xj's are either 1 or 0. This is for one particular example. And then if you take it on average, so for example, you could do the average by doing a big sample size of size m, and you could sum from I equals 1 to n, sum of j equals 1 to k, and then you would do xji, and this is the ith sample class j, ith sample in class j, times the log of p hat j, and this is totally the multidimensional analog of what we had before up here, of saying you can add up xi and 1 minus xi. Notice, right, here it's just a sum from I equals 1 to n, and here I could have written a sum. I wrote these two terms, I just wrote out the two terms. I could have written it as a sum from j going from 1 to 2, and there's only one variable because the other variable is automatically 1 minus the first variable. If you are class 1, you're automatically not class 2, and vice versa. So even though there are two possible outcomes, I can write it with one variable in the very special case that it's either heads or tails. If there's 3 outcomes, you really need all 3 outcomes. So that is what the generalization is. This formula becomes this formula, and then if you take the theoretical average, so the xji's are either 1 or 0, but on average, they're going to be the true probabilities. So this will be the sum from j equals 1 to k of pj times the log of p hat j. So that's the sort of multi-class cross entropy. And this one, again, is used all the time in machine learning and all sorts of things. Anytime there's classification, this is a super important thing. So the multi-class cross entropy loss. Okay, very nice. That's the answer to the mathematized question that bamboozled most of you. Where did it go? Yeah, how many people got it right? Just under, more than half people got it wrong this way. 10% of people got it wrong because they were asleep, and then 38% of people got it right. Okay, very nice. Any questions or comments about this idea? The multi-class cross entropy loss. And once again, when you train multi-class models, you measure how good you're doing using the multi-class cross entropy loss, and then you minimize that loss function. You minimize what this is. Oh, I will say, there's a mistake. There's an important mistake on the board. Who sees the important mistake? I told you guys I would make the mistake, and now I made the mistake.
Should we P hat?
No, the letters are correct. The p's and the p hats are in the right spot. It is the sum from I equals 1 to k of pi times the log of p hat I. That is all correct. But there's something that's not. There's a way in which this thing is different than the sum of the squares. What is
It should be minus.
It should be minus. Yeah, very good. So if it's going to be a loss function, it needs to be negative this. The loss function is negative the log likelihood. So you can fix it by saying, how do you write the log likelihood? And then it's this formula. Or you could say, how do you write the loss function? And then you have to include a minus sign. And you'll notice in what I did, right? When I did the example before, there was a minus sign, right? I took the log likelihood and it was negative the square in the real case. So this is the log likelihood, and the loss function is negative this. So this is the multi-class cross entropy log likelihood. Let's fix it. Log likelihood. Okay, and the multi-class cross entropy loss, the CE loss, is negative that. Sum from j equals 1 to k minus pj times the log of p hat j. It's very important because if you minimize or maximize, you can get that wrong in your code and everything will fall apart and nothing will work. Okay, fantastic. Questions or comments about this multi-class thing? So now the question is, we have a measure. If you were giving me p hats, how could I come up with how good or bad we're doing, right? So either given some data, we add it up like this, or given the real p's, we do it like this. Those are two different ways that we can actually use this in practice to calculate how good or bad we're doing for a given set of p hats. But the question is, how do we come up with the p hats in the first place? So last class, we used the sigmoid function. How to make p hats. And last class we did it in binary classification, we did it with the sigmoid. We did p hat equals sigmoid of x, or maybe I'll call it y, because x is usually the input, which is e to the y over 1 plus e to the y. And this sigmoid function converted some real value into a probability, right? And by the way, 1 minus p hat, that was the sigmoid of negative y, right? Which is like this, 1 over 1 plus e to the y. So the y tells you how much you should put into the e to the y. And if it's large, then you have a probability close to 1. And if it's small, you have a probability close to 0. And we estimated y with linear regression, y equals beta x last class. And now the question is, when you have multiple p's, how should we do it? So if we're going to have p hat 1, p hat 2, and p hat 3, how are we going to, in 3-class classification, how do we do this? Because the sigmoid, it doesn't have 3 parts. So what do we do? And once again, we're going to basically do a cheat. The p hats are numbers in 0, 1, they're probabilities, numbers in the interval 0, 1. And we're going to do a cheat and convert these using numbers that are like the y's in minus infinity to infinity, y1, y2, and y3. And y1, y2, y3 are going to tell us how likely we should make p hat 1, p hat 2, and p hat 3. So if y1 is really, really big, then we're going to make the p hat 1 really big. If y2 is really, really big, then p hat 2 will be really big. But really big means different things. Really big here means large and positive, and really big here means close to 1. Really small here means close to minus infinity. Really small over here means close to 0. And so the question is how to convert. How to convert. And this was mentioned in that multi-class video. These numbers, by the way, these are called logits. The logits, or the logits. I don't really know why they're called logits or logits. The log its. Let me think. Well, there's something with a log, but I don't know. It's just a funny word people invented for these things. These are the logits, and these are the probabilities. And almost every system in machine learning uses logits and then converts them into probabilities at the last second. A good example is when you are talking to ChatGPT. ChatGPT computes the logit for each possible letter that will go next in the sequence, and then it converts those to probabilities before it samples to output an actual letter, and then it does this over and over again to make a long paragraph. But logits and probabilities. And the question is how to convert. And as always, I have a mathematize that will tell you how to convert between logits and probabilities. Multi-dimensional sigmoid. Okay, we need a multi-dimensional version of the sigmoid. So here is the thing where we have 3 classes, class 1, class 2, class 3, and the y values, the logits, came out to 1.5, -2, and 3. How are we going to convert these to the probability of class 2? And I have a few different examples, a few different possibilities. if you watch the video and have good notes, you'll see it right away. But if you don't, you should be able to puzzle through what could it be for class 1, class 2, class 3. Which of these could possibly be correct? Okay, I will open that up for a few minutes. Okay, get in your final guesses here. Let's see if we can see how to convert this. Reveal counts. Okay. All right. Nobody fell for e to the minus 2. That's very good. E to the minus 2, if you do e to the minus 2, there's no guarantee they will sum to 1. So this is part of what we need to do, is we need to make sure that the probabilities sum to 100%. So this is one thing we need to do, is p hat 1 plus p hat 2 plus p hat 3 should sum to 100%. So this should be equal to 1 equals 1. And so if you just do e to the minus 2, like if you just take exponentials of these things, it will not sum to 1. You got to divide it by something. And then the question is, what is the something? And let's see, where did we go? Okay. So 5 people were sort of like, oh, you just take the ordinary sigmoid. So you do e to the minus 2 divided by 1 plus e to the minus 2. And if you did that, you would have, what were the numbers we had? 1.5, minus 2, and 3. And you would convert this. These are my y's. And then this would be converted to my p's. You would get e to the 1.5 divided by 1 plus e to the 1.5, e to the minus 2 over 1 plus e to the minus 2, and e to the 3 over 1 plus e to the 3. And those do not sum to 100%. The problem is the denominators are all different. So you have these 3 different denominators, so you add up p hat 1 plus p hat 2 plus p hat 3. They don't add up to 100%. So unfortunately, that one is also wrong. That one is also wrong. This one's not right, which leaves us with the 2 most common categories, this one and this one. And these ones, they will have the same denominator, right? This one is the same in all 3, right? For class 1, class 2, class 3, it's the same thing. This one is also the same thing, but which one is right? Which one is right? And I will, as always, if I just tell you the answer, I think it was more instructive for you to think about why the answer is the way it is. If I just tell you, it's not as good. Let me open it up again for a revote, and you will tell me. Okay. Okay, I'm going to open it one more time. I want this problem, and I want to repeat it. Okay. Okay, it is open once again. See if you can figure out what's going on. I will remind you, in the previous question, the majority got it wrong. So don't be fooled by the majority. That is not a good reason to choose a particular answer. Okay, let me do 15 more seconds here to get the last stragglers in. Because there's one person. Oh, okay, all right. I think we're at 21. Okay, 20. Okay, good to know. Okay, let's see what people did. Oh, okay. Big majority in this one, 15-6. That is the correct answer. One person is still asleep. Oh no. Okay, this one's right. Why is there no 1 plus? This is actually the same exact thing we did before, where there was no 1 minus p, right? So in this situation, they will all add up to 100%. If you do the 1 plus, that is kind of like adding on another class that always has a 0. So this would be like if there was a 4th class, and you're like, I'm always going to make the logit for that class 0, then you would include this one. And so that's what people do a lot. Sort of when we were doing the original, the binary classification, there's 2 classes, and one class is the opposite of the other class. So you can kind of just like pretend there's only one class, and whenever you need to do the other class, it's like automatically included for you. When you have multiple classes, you usually don't want to do that. So the formula is not this. The formula is, in general, y becomes e to the y over, and then it's the sum of all the things. Let's say I equals 1 to n. Yeah, I'll just write it as a formula. P hat I is this guy, and then I'll sum from j equals 1, e to the y j. Okay, and this makes sure that it sums to 1, and bigger ones are bigger. This is called the softmax function. This is another very important thing used in machine learning all the time, the softmax function. And don't mix it up with the 1, right? So it's kind of the sigmoid, the multidimensional sigmoid. Let me write it like this. So softmax, this is softmax I. Let me write it somewhere else because it's not fitting here. Okay. 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 So you have your logits. You apply the softmax functions to all of them. The softmax is a big vector of probabilities, and you choose the ith one. And I will tell you how it's related to the sigmoid. The sigmoid of x is the softmax, the first component of the softmax, where you do x and you put in a 0. So if you always put in a 0, then the sigmoid will be the first component, and 1 minus the sigmoid will be the second component. The 1 minus the sigmoid of x is equal to the sigmoid of minus x, which is the other component, the softmax of 2 of 0, x. So this is the softmax function, and it's used in all sorts of models. I don't want to switch them twice. You switch them once, and then it's fine. Okay, x comma 0. Okay, so this is e to the x over 1 plus e to the x, and this is e to the 0 over 1 plus e to the x. Very nice. Okay, softmax and sigmoid, multi-class classification. Okay, these are very useful in real life and used in all sorts of places. And this is essentially all I wanted to say about logistic regression. These are all the details that are different between logistic regression and linear regression. Logistic regression is just linear regression with these little things built on top. So the cross-entry loss and the softmax. So I'll write it as a sort of a math equation. Logistic regression equals linear regression. And then what you do is you replace, so you do plus cross-entropy loss, and then you do minus square loss. So you replace the square loss with the cross-entropy loss, and you have to do a softmax plus the softmax, or the sigmoid applied to the y's. So the betas, you do y equals beta times x, and then you do p hat equals sigmoid or softmax times y. to get the p-hats. So that's like the basic formula. And that means that anytime you're doing logistic regression, it's going to be somewhat similar to the linear regression, which we already did, and is very similar in a lot of ways. All the things we talked about before, all the things you're doing in your project now, will apply to logistic regression as well as linear regression. Any questions or comments about this stuff? So we're going to move on. More classification. All of these things are based on the log likelihood. The log likelihood. And they're all based on maximizing the log likelihood. Maximizing log likelihood. There is a slightly different way of doing this kind of thing, and that is kind of the Bayesian way. This is what we're gonna move on to now. This is a different way to do it. That is not the same, different way, and that different way is the Bayesian way. And very roughly, what is the Bayesian way? We want to know the probability of a given class given X. And this is hard. This is what we've been doing the whole time. And this is what the logistic regression says. It says the probability of the class, well, we find the parameters that maximize the log likelihood so that the probability of the class is as high as it possibly can be. But the Bayesian way says, there's a different problem. We could solve the reverse. We could maybe figure out the reverse. Maybe do the reverse. And in the reverse, it's the probability of some observation X given the class. And this is sometimes easy. I'll say easy. Sometimes. And I'll give you an example of this kind of situation. So in other words, instead of trying to figure out the probability of a class given some observation X, we say, in a given class, what is the probability of observing some given X? It's the reverse thing. And then we do one more trick, which is Bayes' theorem to reverse it. Use Bayes' theorem to reverse it. Okay. And depending on, these are all different Bayesian ways. This is the high-level Bayesian way. Depending on how you exactly compute this probability, so the easy, you will get lots of different methods. So the linear discriminant analysis is some particular estimate, linear discriminant, or quadratic discriminant. These are all different methods for estimating this probability of X given the class. And they all fit under the umbrella of Bayesian methods, which say, first you estimate this, and then you convert that into the thing you actually want. And that is a little bit different than what we did before. What we did before was all likelihood-based, so we never got into this conversation. We were just maximizing the likelihood on this. And now we're doing this second problem. That's like the high-level idea. And what we're going to do is we're going to do an example. Yes, an example. And in the example, you will be able to calculate this thing exactly. Let's do the example. So what is the example? It's in Mathematics. Okay, here's the coin. There are two coins in a bag. One of them is a regular coin. Regular coins, as you know, have one side which is heads and one side which is tails. The other coin is a double-sided coin. It has heads on both sides. So there's a type heads-tails coin and there's a type heads-heads coin. These are the two classes in this problem. You got to classify, is a given coin, is it a type heads-tails, or is it a type heads-heads? All right. You choose a random coin from the bag. You look at one side of the coin and see that it is heads. This, by the way, is like the x value for the problem. So the x value is our observation of one side of the coin. That can either be heads or tails. So given this information, what is the probability that it is a type heads-tails coin? What is the probability it's a type heads-tails coin? This is a classic Bayesian problem. If you had a good probability class, you've definitely done problems like this, and you'll have no problem with this one. Let me give you 2 minutes to puzzle this one out and see if you can figure out what it is. If you can remember, what is the solution method for this type of problem? Okay. All right, just a few seconds left. Get in your guess on what you think it will be. Okay, let's see what people said. And I guess, is the timer still running? No, okay, good. Okay, out of 21 people, lots of different votes. A quarter, a half, 0.125. A half is a very good guess because there are 2 coins in the bag, and one of them is the heads tails coin. So 2 coins in a bag. What's the chance it's a heads tails coin? Seems pretty reasonable. It should be a half. Someone also wrote 0.5 down here. 0.5. 0.5. Hey, there we go. 0.5. So 5 people into 0.5, but 7 people are in a third. Some people also 0.33. Maybe they also meant a third. And that is the correct answer. So it is indeed 1/3. So what is going on here? Why is it not a half? It seems like it should be a half. 2 coins in a bag. You pick one at random. But it's not a half. It's a third. Let's draw the picture and solve this problem. Okay, so 2 coins. 2 coins. And the way I organize this is I think of a probability tree. I'm going to draw a little tree here. And there's 2 things that can happen. Either you pick the type heads tails coin, or you pick the type heads heads coin. And this is indeed 50%, 50%, 50%. So this is the start. In general, you will have classes, right? In general. Yeah, so this is our example. Yeah, this is in general. In general, you have many classes. There's some class information. There's class 1 all the way up to class K. And for a given point, it could be any one of these classes. But the interesting thing is that we don't just have to predict the class, is it a type heads tails or a type heads coin on its own. We have some extra information. And that extra information is the sort of observation of what we see. And this is an extra layer on the tree. In this case, the type heads tails coin could yield a heads or a tails, each with 50% probability. But the type heads heads coin is a heads or a heads. Okay. And in general, every class has different observations that come with it. And they have different chances for different things to happen. So this layer is the sort of class layer, the class layer. And this layer is the sort of observation, or the X layer of the probability tree. The X layer. Observations. And depending on the class, the probabilities can be very different. So maybe class 1, you observe one thing very often. And class K, you observe something else very often. Right? So the probabilities here are very different than the probabilities here. In our particular case, the heads, tails, and the heads, heads, the tails is completely different. If you see a tails, it's for sure the heads, tails coin, because it's impossible over here. So the distribution of the kinds of things you see are different. I wrote it as 50% heads, 50% heads, but I could also, maybe it's more clear and more instructive to write it like this. I could write it as heads and tails to keep it consistent. And I could say tails is 0% likely, and heads is 100% likely. So the thing that separates the heads tails coin from the heads heads coin is it's more often heads over here, and it is less often heads over here. It's more often tails. This is like the kind of thing you see in real life. You have many classes, and the kinds of observations you see from the different classes is different. Okay, but we have to answer our original question, which is, what is the probability, the coin, what is the probability the coin is a type, what did I say? Heads, tails coin. Heads, tails. Given our observation. Given our observation. And this is the part that I think throws people off for this question. Given our observation, we're calculating a conditional probability. So we're doing, in general, what we're doing is the probability of seeing some class K, given the observation X. And in our probability tree, we kind of have the reverse. We have the probability of the X's given the class. We know the probability of heads and tails when you're in any particular situation, and we kind of have to reverse it to find the probability of type heads, tail, given we saw a heads. Okay, there are many ways you could do this, but the simplest way is to just count on the tree. So this is, by the rules of conditional probability, this is the probability, it's a type heads, tails, and we see a heads. We see a heads. So both divided by the probability we see a heads. And the thing is, on the bottom, there's many ways we can see a heads. We can either see it from a type heads, tails, or a type heads, tails, or heads, heads. So to count this, we can look at our probability tree, and we can say type heads, tails, and a heads is this thing. That's the top of the thing. But the bottom has two ways. So the we see a heads is actually two different ways. It can go like this, or it can go like this. So it's the ratio of those two things. Another way to say it is we have cut away these two branches. We saw a heads, so it's definitely not one of those two branches. We can cut those away from our probability tree. So what are the probabilities? Well, we use the multiplication rule, 50% times 50% for these trees. So we multiply the 50% times the 50% for that branch, and then 50% times 100% for this branch to get the final answers. So the answer is 50% times 50% divided by 50% times 50% plus 50% times 100%. So in other words, you can calculate the probability of every individual branch. And we're doing this orange branch divided by the sum of these two green branches. And that's what it is. Okay, what does this work out to be? This is a quarter divided by a quarter plus 1/2, also known as a quarter divided by a quarter plus 2 quarters, which is 1/3 after you simplify the quarters. And really, I think this is a nice way to see it. There's a 1/4 chance you have the type heads, tails coin and you saw a heads. There's a 1/4 chance you have the type heads, tails coin and you saw heads. But there's a 1/2 chance you picked the type heads, heads coin and saw a heads. So because the type heads, heads coin has way more heads, it is sort of overrepresented over here. And that is what's causing it to be 1/3 rather than a quarter. It's higher than you think. Sometimes people forget this thing. So that's one way to do the problem. The other way is to use the Bayes theorem. And the Bayes theorem tells you the reverse. You can do the probability of A given B. You can write that just as a straight formula in terms of the probability of B given A. And what you have to do is you have to scale it by the probability of A divided by the probability of B. So that's the Bayes theorem from basic probability. And this lets you do the little reverse-a-roo sort of mechanically. Let's do it this way as well. So if you do it this way, then the probability of a type heads, tails, given we saw a heads, it will be the probability of type heads, tails with no information divided by the probability we saw a heads times the probability of the reverse. You see heads, given it's a type heads, tails. Type heads, tails. And the point is that this last probability, the probability that you see a heads, given that it's a type heads, tails, is very simple. That's 50%. That's like really well known. So this is 50% because of the coin has one side of each. So this one is really easy to calculate. This one is hard to calculate. And Bayes' theorem says something hard in terms of easy things. The probability of type heads, tails is 50% because there's 2 coins in the bag, and one of them is the type heads, tails. And then last but not least, we got to do the probability we saw the heads. This is actually quite annoying because you have to sum up, again, over the 2 paths. So sort of the hardest part of this whole kit and caboodle over here is this bottom bit that we saw at heads. And that one is, again, the green paths. Those are all the ways we can see heads. So we have to do the same calculation that we did before. It's a quarter plus a half, same quarter plus a half as before. Let's try again. 1/4 plus 1/2. And you can see the Bayes theorem is giving the same exact answer as before. It's just a different way of organizing it. Sometimes people prefer it this way. To me, they are totally equivalent. There's no difference at all. This is, again, 1/4 divided by a quarter plus 2 quarters, also known as a third. Okay, so classic problem. And it kind of shows you that when you have information, when you get information from the x's, it will change the probabilities of the classes, and that's exactly what you're trying to do in Bayesian classification. So this example problem is kind of a warm-up on this Bayesian classification thing. Any questions or comments about the Bayesian classification thing? Okay, we're going to have lots more about the Bayesian classification. Like I said last time, depending on how you choose to do this estimating, the probability of x given the class, you have many choices for how you do it. If you do it one way, you're going to get something called linear discriminant analysis. If you do it another way, you'll get quadratic discriminant analysis. If you do it another way, you'll get something else. There's many different. You can do it with nearest neighbors. You can do it with lots of different ways. So basically, the Bayesian classification is a method to convert this kind of calculation into that kind of calculation, and you have lots of choices to do this. We'll see some of them in class next week, because there's no next Wednesday, because there's no class on Monday. Okay, questions or comments about any of this stuff? Okay, we have a couple extra minutes, and there's an activity that I have been saving that we're going to do now, because we have time for it. And this activity is going to answer the question, why the hell do you give us so many mathematized questions? That's going to be that's what we're going to answer that right now. Okay. So let me open it up. I have to do this and then this. Okay, so this is a different poll. So you're going to have to put in different letters. Q, X, Y, O. It's a different one, not the same as the one we were just in, unfortunately. And then when you guys are ready and you're in, I will bring this up. Okay, let me pause this. Don't look at it yet. Okay, we're going to go back to this one to pause this. We're going to do the thing. Okay, is everyone ready? Everyone, put your hand up if you're in the QXYO. Okay, people are in. So here's the problem. You don't even need to be in the poll yet. But we're going to take 45 seconds. Don't do anything else. No typing. Nothing else. 45 seconds, and just look at the list of words. That's all you have to do. 45 seconds. I will, as usual, keep time with the timer. Okay. Okay, time is up. Let us now go to talent code part 2. What does part 2 say? Part 2 says, write down as many pairs of words as you can remember from the words that were displayed. So you stared at those words for 45 seconds. Write down all the ones you can remember. You can either write it on paper or you can type it if you're typing. But you should have a list of all the pairs that you remembered. Okay, you can hit ready if you're ready to let me know to move on. But first write down as many as you can remember. Okay, who is still writing words? Who's done writing words? Put your hand up if you're done writing words. Okay, everyone's done. I only have 12 answers. That's okay. I'm going to assume that you're able to get in. But let's go to part 3. Talent code part 3. Here we go. So of the words that you guys were looking at, I organized them into 2 groups. This group over here, these were completed words. And these ones, I very annoyingly put a blank in part of them. And now the question is, which set of words was better for remembering? Which one was better for remembering? And the way we're going to measure what was better for remembering is what I want you to do is on your list of words you remembered, count how many came from column A and count how many came from column B. So you have, I remembered these words. Check and see, are the words you remembered, did you have more from column A or more from column B? Okay, I have to show you the columns so you can see them. There's the columns. And the choices are, you had more from column A or more from column B. Did you remember more from A or more from B? Okay, good. Make sure you put it in. Okay, I'm up to 10 answers. Make sure you put you have to press the button on which one, A or B, you remembered more from. Okay. Now we're up to 16, 17. All right. Very good. Okay. So this is a really interesting exercise. Obviously, the difference between these columns, these are complete words, and these ones are missing something. And there's kind of 2 ways you can think about learning. You can say, when you're learning, people tell you the knowledge, then you memorize the knowledge, then you know the knowledge. That would be a column A is better. See, column B is sort of defective. I didn't even tell you the whole word. So you might think column A is better for learning. Let's see what you guys said. So who remembered more from which one? Reveal. Wow. 15-5, people remembered more from column B. So the thing I just said about column A is better for learning is totally bullshit. This is not how people learn. People don't learn by you memorize it, then you know it. That's how a computer learns. You're not a computer. You're a human. Column B is way better for learning. How could column B possibly be better for learning? It's missing some of the information. I didn't tell you the answer. I said you figure out the answer. How could it be that B is better? What is the explanation based on what you know about humans?
Because you're putting in effort.
You're just putting in effort. So when you were a caveman, you were looking around and there was all sorts of stuff you could pay attention to. And the things that you spend effort on, those are the things you remember. If you spend a lot of effort picking berries, you're like, I'm going to come back here and get more berries, okay? So the way your brain works is when you put in effort doing something, that is how you learn it and remember it. And that's just the way your brain works. Your brain does not work by just like passively sucking up words. You have to do the effort. That is why I give you guys a lot of mathematized questions in the class. I could just give you the formula, say, here's the formula for a multi-class logistic regression. Here's the formula for this, right? Instead of doing that, I say, you figure out the formula. You give it a try. I'm doing the fill in the blank. And then I tell you what letter was in after, right? So I say, hey, this was actually supposed to be an O for river boat. But now that you've tried it, maybe you'll remember it better. So that's why we do the mathematized in the class. Fun little exercise on why we do it. And hopefully it helps you appreciate the stuff. On Friday, your draft is due for Project 1. I have office hours Friday morning if you want to come by and hang out. What else to say? Monday, there was no class. Please do not come on Monday. You will be sad. On Wednesday, we'll have the next class. Yeah, question over here.
Maybe I missed it, but how do we turn it in?
Oh, yes. Okay, this is a good point. I also posted last night how to turn it in.
Oh, okay.
Let me show you the link and make sure it's actually live. So there's a link that I added last night, which takes you to the PAIR tool. PAIR stands for Peer Evaluation and Response or something. And this is the system. You'll submit it, and then you will also go there to get 2 other people's to review. So this PAIR tool, it looks like it's from the 80s. It's an amazingly old piece of technology. But if you go down here and you log in, you will be able to submit your document, And then you will also receive other people's documents to review. That'll all be done on the pair tool. Remember, this is all for learning purposes only. We don't grade. You're not going to get a grade for this beyond did you put in a good effort in reviewing other people's things. And it's all on the pair tool. Yeah, that's a great question. Yeah. It's always annoying to set this up, so I procrastinated it till yesterday, but it should be there now. Okay, fantastic question. Any other questions or comments? All right, fantastic. I will see everyone on Wednesday. Have a fantastic long weekend, and we'll see you next week.
Professor?
Yeah.